with your support, we've been able to make this conference free this year. And first up in the line is John Lockwood from Algo-Logic. John.
Hey, Raj, how you doing?
Good, thank you. I will save the intro, so give you more time. So please go ahead.
Okay, can everybody see the slides now?
Yes.
Yes, excellent. Okay, so this talk is going to be about using algorithms and logic to get ultra low latency networking. In particular, talking about doing full stack applications that run in field programmable gate arrays. And so a quick outline of this talk is, first of all, who are we? Algo-Logic Systems. I think those of us at Hot Interconnects, we've been around for a long time. I think the first talk we did on this was 1999. We'll talk about some of the products and solutions that have been developed and some of the applications and customers that we have now. And for these algorithms and FPGA logic, really well suited for things like accelerated trading. And so as it turns out, for doing tick to trade, as Head Bubba knew years ago, is that to be competitive in the trading market, you had to have the fastest technology. And FPGAs have turned out to be a really good technology for making tick to trade systems, implementing pre-trade risk checks, and even building stock exchanges. And so we'll talk about these products that we've built, as well as some of the other peripheral products like our key value store and our packet classifier that we've recently implemented with high-level synthesis. Throughout this, keep in mind that Algo-Logic is a company that puts algorithms into logic, is that we have these development frameworks that actually run on off-the-shelf partner platforms. And so in particular, we're using cards that come from the Intel, from Cisco and Xilinx. And I'll go into some detail on the actual platforms later. But all the solutions we're talking about are multi-platform and provide similar latency across different devices. And so mapping algorithms into logic is something that started for us back in 2009. And so Algo-Logic is a privately held C corporation. It was a spin out from an effort that we were doing at Stanford University on the net FPGA. And it was really motivated to productize these fintech products. In fact, by a discussion with Head Bubba and Raj, and also Andy Bach at NYSE, when they came out to Silicon Valley from New York to talk with us about the kind of things they needed in their switches and networking devices. And so Algo-Logic is based in Silicon Valley, but we have a lot of customers now that are in New York and Chicago and around the world for other exchanges. So our products and solutions are FPGA IP cores that do ultra low latency networking. So this includes things like our ultra low latency MAC, a TCP endpoint, a UDP endpoint, and a match engine, which is an associative lookup engine. We also now have these complete FPGA solutions that allow accelerated finance and real-time data applications. And so we can use these IP cores, the frameworks, and we can build full stack development applications that allow our customers to trade on NASDAQ and CME and many of the other exchanges. So our customers are banks, prop trading firms, stock exchanges. We also now are selling equipment to, or IP cores to data center equipment providers. And we also assist with companies that do real-time data acquisition and help them implement their cloud solution for that. So just a quick overview of our development framework that runs on a SmartNIC. And so really at the center of this is an FPGA card. And so Algo-Logic is these red blocks that go around it. And so this includes Ethernet, UDP, TCP, associative lookup engines, and this business logic that implements the actual trade strategies that customers use to trade on exchanges or do lookups. There's also a software component, is that customers typically start with a bunch of C or C++ software, and we provide them an API so that if they want to just treat the hardware as a black box, is that they can use it through an API, or for the more advanced customers that want to write their own applications, is that with the high-level synthesis compilers, we help them integrate with our IP cores so they can actually be writing logic that will synthesize into the FPGA itself. And so it really turns out to be an ideal solution for low latency networking. So this FPGA card usually consists of this PCI Express bus, a fast data mover, or a low latency kernel bypass NIC, so that when you do want to get data between the FPGA and the processor, that you can do that across an interface with low latency. And now with high-level synthesis, the ability to compile applications that run in logic starting from C or C++. And so what Algo-Logic is providing is all the infrastructure and framework around these cores, including our MAC and our TCP, our cut-through data processing applications, and our APIs so that C and C++ programmers can quickly get into FPGA acceleration. So this turns out to be a really great solution for high-speed trading, pre-trade risk checks, and order gateways. And so as you can see, kind of the slowest way to go through the system, but still pretty good, is if you have network traffic that's coming in and goes up through the PCIe bus to an application software program, comes back down to the card and goes back out. And so for that, you want to take advantage of a low latency PCI Express with a low latency data mover or a low latency NIC. But you can do better, is that if you've got TCP flows that you're processing, by having the entire stack offloaded to the card and into FPGA logic, we can actually implement stream level processing functions that run directly in the FPGA logic. And then even faster is that if we end up doing things just on the packets themselves, we can do packet processing directly as packets stream in and stream out, and get the full benefit of cut through ultra low latency, nanosecond type latency timeframes. And so just to give you some ideas, that a typical NIC has typically microseconds of latency, and that's now there's kernel bypass optimized latency NICs that get down to the single digit microseconds of latency, and with a low latency firmware pushing around a microsecond of latency. And so that is for the time it takes to go up to the host and come back. But with the Algo-Logic solutions is that we look at building applications that run entirely in logic. And so with this and with our IP cores, we can allow doing flow processing in the deep sub-microsecond, nanosecond regime, and also do packet processing in this very small number of nanosecond regime. And so these kind of applications that are processing in hardware, FPGA logic instead of software, have the benefit of being completely deterministic. And so by that, I mean that 100% of the packets that come in go back out of the system in a finite amount of time, which is measured in nanoseconds, as opposed to when things involve software in the PCIe bus, there's typically a tail latency. And so some things are relatively fast, like microseconds. Some require tens of microseconds, but sometimes the tail latencies go all the way down into milliseconds. And so this is the battle that we're trying to help our customers fight, is to get their applications to run on the left side of the graph where the latency is low, instead of the right side of the graph where it might take a long time. And so in the evolution of trading systems is that we've seen customers start off as being humans that used to trade in the pit, and trading on behalf of their clients at an open outcry, is that they could get trades done in minutes and even down to seconds using clever hand signals. But this quickly migrated over the past few decades to automated trading systems where desktop computers were used to automate the algorithms for trading. And this brought the trading latency down from seconds down to milliseconds. But it kept going, is that trading on a desktop evolved to putting servers into hyper-optimized data centers using kernel bypass. And this brought the trading latency from milliseconds down to microseconds. And that's pretty much where most of the people are today that are still trading in software, is in single digit microsecond regime with their servers just meters away from the exchange by being the co-located data centers. But that's not where most of the HFT trading happens now, is that FPGA acceleration has changed the game for most traders, is that by putting algorithms into logic that can offload the trading algos, we can get the trading latencies down into nanoseconds instead of microseconds. And so this is the competitive edge that our customers have, both those that are doing the banks that are providing risk checks, as well as the prop trading firms that are doing the trading themselves. And so our framework for accelerated trading looks something like this, is that we have stock exchanges that are and customers that are trading stocks, options, futures. It's starting to see some crypto trading happening. And what typically happens from the exchange is that we have market data that comes in. That market data is carried in UDP packets. It goes into the business logic. We make decisions on how to place orders, and those orders get placed out on TCP flows, and they go back out to the exchange. And by doing this entirely in the FPGA with the business logic compiled to hardware, we're bringing this latency down to nanoseconds. And so, of course, customers still have a big base of software, things like connecting to the exchange, authenticating, the non-latency critical functions. All that is still operating in C or C++ software, and it can talk to the FPGA card just the way that a normal NIC would talk to the card. It's just that for these latency sensitive trades, we can offload that to hardware so that the customers get the really good latency. And so to put this in perspective, back on that latency chart, we can see, for example, with banks that were running pre-trade risk checks and using software, that was taking milliseconds down to microseconds of latency. For the prop trading firms that are using the kernel bypass NICs, really the best they could do would still be down in the microsecond regime. Single digit micros, sure, but still hard to get that less than a microsecond. But by putting the algos into the FPGAs, we're able to get the tick to trade latency and the risk check latencies down to the nanosecond regime. And that's where we are now. And so one of the challenges is how long does it take to bring up a system like this? And so in the past is that if you started from scratch, is that such an effort could take, if you didn't care about latency, if you're just latency aware, as many kind of mutual funds and hedge funds are, is that you could pretty quickly just go online and go trade without making any optimizations. But as soon as you became latency sensitive, you needed to start concentrating on how to lower the latency. The effort became days and weeks. And then if you wanted to go into hardware acceleration, that effort really accelerated. And instead of being a few weeks of effort to change some software, it became months or years, and in some cases never. Because once you get down into the latency critical where the HFT traders are, you can be down into FPGAs, custom ASICs, and pure hardware. The HFT group is demanding. And so the battles over nanoseconds can cause projects to go on for a long time. And so Algo-Logic is the reason for this company's existence is to help those people that need to get low latency, but still need to get a product to market, get their trades going quickly, is to provide a solution which has both quick time to market and ultra low latency. That's kind of a sweet spot that we operate in there. We've done other things, as you've heard from some of the other talks that we've given in the past at Hot Interconnects, and we've done efforts like our key value store. And so recently, one of the efforts that we did with on a Dell server was to push 500 million IOPS into a 1U Dell server. So this was on a 2-socket server that was running the Redis database and software and had a SolarFlare NIC. But what was added was 3 Xilinx Alveo U50 cards. And Algo-Logic's key value store was loaded onto each of those Alveo cards. And we uplinked all of these FPGAs directly to a top of rack switch. And so by having a mix of having Redis traffic go to the processor sockets and having our key value store functions go directly to hardware on the FPGA cards, we were able to allow client applications that were on the other side of the network run C++ applications with the standard API and send commands through like gets and puts and inserts and deletes of key value pairs and push a 1U system to 500 million IOPS, 500 million IOPS, which is a pretty big number for a 1U server, but certainly possible by having these things offloaded to hardware. Another recent project that we've done is that using the high-level synthesis on Intel's HLS is that we implemented a packet analyzer that takes network traffic that comes in, and it uses the FPGA to do packet classification, and it keeps track of the stats of the packets going through so that software can just monitor the number of packets. And the deep packet analysis is being done in hardware while the stats are being brought over the PCIe bus to software. So completely offloaded the work of processing the packets and just let software deal with the stats, which is what it needed. And so this really was a good application for the Intel HLS compiler in a sense that you could have the full flexibility of writing C and C++ programs, but be able to compile that and still run it in the FPGA logic, interface that with the Mac. So some of the platforms that we're currently using today include from Intel, the PAC D5005, so a Stratix 10 with on-chip SRAM, DRAM, and 8 ports of 10 or 25 gig Ethernet. We also work with Cisco, as that we're a partner with Cisco, and use their SmartNIC V5P, V9P. That was the former Exablaze product. And so on that, we have our trading framework, and that supports making use of the on-chip and off-chip SRAM. The card also has DRAM, and again, 8, 10, or 25 gig ports. And with Xilinx, of course, the Alveo platforms, the U50, U200, U250. And what's neat about the Alveo platforms is multiple different form factors from the size of a GPU down to a half-height card, and also including HBM memory. And so a good mix of not only on-chip SRAM and DRAM, but also HBM on cards like the U50. So in conclusion, the there are solutions that enable ultra low latency networking. This allows customers to leverage their existing base of software that's already running in the CPUs and their kernel bypass NICs, typically written in C and C++. And we can help them migrate some of their time critical functions to run in the FPGA. So Algo-Logic's products we have include our low latency MAC, our UDP, TCP networking stacks, the associative lookup engine so that traders can keep track and associate opportunities with trades. And these full stack applications that include the complete offloaded application, kind of the layer 7 function implemented in hardware that does the trading, the database function, and processing of the real-time data. And so these reference platforms leverage our tool vendors, high-level synthesis frameworks, so the Xilinx and Intel HLS frameworks, which have come a long way over the past decade. We use these off-the-shelf FPGA cards, is that Intel Altera, Cisco Exablaze, and Xilinx SolarFlare, kind of best of breed technology. And so our apps just run on top of all of these platforms. And these operate in pre-qualified systems that can be purchased directly from the big name vendors like the Dell and HPEs, where they have pre-configured, pre-tested cards that can be bought along with the systems. So if you know somebody that's trying to be more competitive in the trading space, feel free to contact us. Our email is solutions@algologic.com. Thanks.
Thank you, John. That was a very good presentation in a quick time. Clearly, Algo-Logic has come a long way since probably 2008, 2009, early days when we first started speaking about it. There is one question in the Slack channel. It's from Dan Pitt, and I think you covered most of it in your session in the talk where you spoke about the key value store. Dan would like to know a bit more about the application context for KVS.
Yeah, so the application context for the key value store was that applications like Memcached need to do get, put, insert, and delete operations, basically the CRUD functions of a database quickly. And so the key value store was something that we had offloaded to the FPGA in the context of our trading systems years ago. And by making that available as a standalone solution is that our customers have been able to make use of the key value store so that they can write client applications and software, but still get the speed of hardware when they need to share the data over the network.
Awesome. Thank you. Thank you, John. Just saying if there's any more questions here, just a second. No, I think we're good. Thank you so much, John. Thank you for all your support over the years for Hot Interconnects.
Okay, thank you.
Thank you. And coming up next, we have TidalScale. We have the CEO of TidalScale, Gary Smerdon. Gary, you're up.
Great, Raj. I appreciate it. Thanks, everyone. And let me share the presentation here. Great. So again, thank you. It's a pleasure to be here and to introduce you to TidalScale and a technology that we have developed called software-defined servers. So you'll hear about in the session about the market need for it, the specifics on what we are doing, how we do it, and also a glimpse at where we're going in the future with our technology. So to start with, we always start with the business need. And of course, we all know that data has become core to every business. And we're also all dealing with how data growth is overwhelming us. And this is really when you look at the end customers, end users, enterprises in our case, that the IT overwhelmingly understands that investment to keep up and stay competitive, to stay agile, and to deal with this data and get the most out of the data is absolutely an imperative for the business. Now, let's take a step back and kind of look at one of the things that has been a key factor in businesses being able to keep up with data growth over time, and that's been Moore's Law. We're all familiar with how it started out with kind of a view of the doubling of transistor count over time. David House kind of redefine Moore's law to be around the doubling of processing capability every 18 to 24 months. And of course, that has led to a lot of things. And one thing it certainly led to was the growth of computers absolutely outstripping most data growth. So servers actually absolutely became more powerful than what most applications needed. And VMware came in and took advantage of that. They really saw that opportunity to create traditional virtualization where we break a system into smaller pieces and run multiple jobs, reducing our server count and maximizing the resources that we have. And of course, the success of VMware was largely driven by no change to the operating system or to the applications. But a lot has changed since they came on the scene, and certainly one of the things that has been a key megatrend is that no longer are we seeing traditional processors being able to continue to grow in their capabilities at the same rate. In fact, if you look over the past 12 years, the absolute performance of CPUs, think of the Intel, AMD, et cetera, processors, that they have missed what was predicted by Moore's law by over 200x. So it's not been a kind of a stub my toe. It's been a huge miss. And of course, a lot of technologies, like you just heard about, are coming in and trying to fill some of these voids. But it's a really big problem. And the reason is at the same time that Moore's law has failed us, data growth is overwhelming us as well. And this has created a gap, an opportunity, and that's where TidalScale comes in. So what we do, think of us as the inverse of VMware. Instead of taking a system and breaking it into smaller pieces, we take standard x86 servers just connected with Ethernet and allow them to be created into a virtual, what we call a software-defined server of essentially any size. Like traditional virtualization, we require no change to the operating system or the applications, and this can be done in a matter of minutes. So for the first time ever, we can create a server to match the size of the data that we are trying to run. And this is kind of a small list of some of our customers and partners from around the globe. So the business benefits and what we provide in creating this software-defined server is first, faster deployment. One of the big challenges when you're talking about data size is getting the right size system. But how do you figure out what the right size system? Few people really understand how much hot data they have today, much less what are they going to have a year or 2 or 3 or 5 years in the future, which is really the planning cycle when you're doing a deployment. So faster deployment, key benefit. Performance is critical as well. And the reason what we focus on performance is around in-memory performance. We're a big believer that data should be in DRAM, okay? Not flash, not any other type of memory, but specifically in DRAM. And the reason for that is DRAM is 1,000 to 10,000 times faster than the fastest flash storage. So, 1,000 to 10,000, that's a huge, huge difference. We're talking about 50 nanoseconds versus 50 microseconds or 500 microsecond type of range. And as I would, kid around with people, that's, if I, tell my wife, oh, I'll be an hour late, that's that may be a problem. But if I say, oh, I'm going to be a year late, that takes it to a different level. And that's the same relative difference. And it matters to a microprocessor in the performance of data. Next is cost. Everybody is focused on cost. By using standard x86 servers, standard building blocks, no specialty systems, we're able to drive down both the OpEx and CapEx cost, as well as have major benefits around minimizing core count licensing as well, because now the servers can be focused on what is absolutely needed for the application, understanding that memory is often the most important factor for getting the most out of the performance. And last is agility, building as you grow, scaling up and down, being able to adjust as your needs change. And so here are some of the metrics that we typically see: 25x faster deployment time, performance from a application standpoint being in memory is often 2.5 times faster using the same core type of processing systems, 52% plus cost savings, and the agility is just absolutely unparalleled. For the first time ever, again, we can now scale systems to meet the size of the data. Now, let me explain a little bit about how we work here, because what I said is that we're using standard x86 servers connected just with Ethernet. So how are we running an operating system and applications and having them run without any modification? So this animation will kind of go through the underlying, under the hood, how we work. What we do in this case, we're taking 4 nodes, 4 standard servers, we boot them up and we create a software-defined server where we virtualize all the resources. And then, as you're going to see, we mobilize all of these resources as well. So you see here, it's operating on one particular node. But what happens when a CPU tries to access pages of memory on another system? It won't see it. And so at that point, we then have a choice. We can either move or copy the pages of memory. If it's just read-only memory, we'll make copies of it across the system. But that's just one of our strategy. Another strategy is shown here is that we will just move the virtual CPU in one jumbo frame of Ethernet. We can move the full Intel processor state to the other system. And so moving the process to the data. We can do that extremely fast and then with, again, only one packet. So these decisions are being made in real time. Constantly, we use real-time machine learning as the brains behind this to have the system be performing optimally. And that's what we call and is the core to what we have as a software-defined server. Okay, but let me show you some real-world kind of the performance of the system here. Excuse me. Okay, so here what we're showing is running an Oracle database. It's just looking at more traditional like TPC-H type of testing, showing a bare metal Intel quad socket system, 768 gigabytes of memory, and the latest V6 generation of processor, 48 cores in this system, and we're using that as the baseline. Next, we're going to take 2 dual socket systems, and in this case, there's actually half the total number of cores, but twice as much memory. And the reason we do that is because we can quickly analyze and see how much memory is required to keep everything in data. In this case, doubling putting 2 systems together, again, actually same number of sockets, half the number of total cores. And you'll also see that we're actually using an older generation of processor, but despite the older generation of processor, we're getting 2.5 times faster. Next, what we're going to show here is basically using those exact same systems. Because we are putting all of the active data in memory, you can even turn on the advanced capability that Oracle supports, which is column store. It's their in-memory capability. It basically makes them perform like an SAP HANA type of application. And as a result, you can see that it's actually 20x faster. Again, same system as in the yellow, just taking advantage of the software, now knowing that everything is in memory. And from a query per dollar standpoint, the impact is even greater, 5x and 30x higher performance as far as queries per dollar. Okay, and this is a real customer example. Global, one of the largest transportation companies in the world. Basically, they had challenges with their SAP HANA application. It was taking too long. They were having trouble getting everything into memory. They're having to break it into a bunch of smaller systems, which is a manual process and very time consuming, and it wasn't getting the business results. What we were able to do is to work with them, and in this case, they have over 100 terabytes of memory requirements. So across 4 different software-defined servers, all the different instances combining to over 100 terabytes of memory, performance increase of 2.5 times, savings of over $3 million. And to them, it was critically important that they were able to deploy faster as well. And now they also have the added longer term benefit is if their needs change over time, they can change the size of the system to go along with it. Okay, so next, just kind of focusing on the memory side again. This is the graph on the left shows in a 6 terabyte server, the number of transistors for DRAM versus the number of transistors for CPU logic and SRAM. And yes, there is actually a number there. That number is a very big number. It's 100 billion transistors for logic and SRAM. But 100 billion compared to 50,000 billion, or otherwise known as 50 trillion, is a very small number. And so these systems are dominated actually from a semiconductor standpoint by memory, which, as we discussed and showed, that's critical to get the most performance out of it. But it now brings another challenge, because memory failure has become the #1 reliability issue with large servers. And actually not with all servers, I should say. And memory errors, of course, have ECC protection, but they go from correctable errors to uncorrectable errors. And uncorrectable errors, of course, is a system failure. And so the next version of our technology and what we are bringing out basically addresses this. So you see, it looks very similar to before. We'd have 4 software-defined servers. Our 4 servers, they're booted up into a software-defined server. The database or application is running on top of it. But what happens in the instance where one of the nodes starts to fail? It's like the warning light in your car. What do you do about it? We will actually bring in another server on the fly. And at that point, we aren't changing to the operating system or the guest what is actually being seen as the size of the system. We then migrate all the resources off, first pushing off the vCPUs, then we are able to pull the pages of memory to whatever node makes the most sense. We pull the IO off as well, because all of the resources has been virtualized. And we can now remove that server that has no longer anything running on it. And doing this with 0 downtime while staying performant. And so, we basically are adding another 9 to system reliability. The uptime of the system is over 100x higher, because now all of the updates and patches, et cetera, as well as potential failures, can be addressed on the fly without taking the system down. So that introduces you to TidalScale, what we're doing with our software-defined server technology. Gordon Bell, of course, famous computer scientist, the father of the mini computer, Gordon Bell Prize and high performance computing named after him. He has stated, and we agree with him, that this is the way that all servers will be built in the future. Have the contact information there for the general contact information, as well as my specific information as well. And if you have any interest, needs, or like to understand more, please let me know.
Thank you so much, Gary. This whole technology about inverse hypervisor is very interesting. Let me see if we have any questions. There's one question here from Ohara Suke. If the total amount of memory is 768 gigabyte for TidalScale configuration, how much impact for performance?
So I'm not sure I understand the question exactly, but let me try to explain again. So when we are running on a particular system, we run as a bare metal system. It's not until we basically see a resource on another system, pages of memory, it could be, is a good example, that we need access to, that there is a system interrupt. This is what happens with any virtualization technology. It's a VM exit. There's hardware acceleration for that makes this very fast. And at that point, we will then move or copy the pages of memory from that other system to the node that was trying to access it, or we can take the process and move it over there in the one jumbo frame. This is a real-time decision that is made. We make these decisions in nanoseconds and microseconds very quickly to continually be optimizing the system. And it's real-time machine learning that we are using to do that. We're not trying to predict the future. We're just trying to understand the access patterns that have been taking place and making those decisions. And we're obviously doing it really well with the performance that we see.
Awesome. Thank you, Gary. There's one more question from Sissy. When you move data between physical servers, will you move through instructions or shared DRAM?
So, so when we're moving pages of memory between the systems, to be clear, we are a highly cache coherent system. It wouldn't work if we weren't. We are not taking advantage and do anything with CXL or anything to do for this. We are doing it with our internal under the hood hypervisor. So if we are moving pages of memory, basically it is just the pages that we are moved. We will, if we believe there are other pages associated with it and that's the right thing to do, we will of course send them as well. But that it's just the pages of memory or the processor state that we're moving between systems. So if I understood your question, that's the answer.
Okay, thanks, Gary. One more question. How do you decide whether to move the VM or the data? It's from Nathan Brookwood.
Yes, so the whole system is one virtual machine. Okay, so we are running one virtual machine. So we're not it's under the hood. So now we're not talking about moving a VM. What we're talking about is moving a process thread. Actually, it's at that level that we are dealing with. So how do we make that decision? We keep track of working sets. That's the whole key to the performance of a system is working sets. You want to have the process and the data as closely coupled as possible. And by closely coupled, by the way, that doesn't mean even on the same server. It really means I should be on the right memory controller within that server because there can be multiple memory controllers in that system. So you can actually get to a sub node level from a working set standpoint. So how we make that decision is we're keeping track of the working sets. If we see that we have a very strong working set that is currently operating, we will just pull the pages to us to keep that working set intact. If we see that it's a weak working set or there's a strong alliance on the other side, we will send the page. And that's part of the machine learning. There's cost functions that are happening, and where when we request or sending a page, there'll be a quick analysis of what's the value to me versus what's the value to you, and that's how the decision is made, Nathan.
Great, thank you. Last question from Dan Pitt. Can you briefly explain the concept of inverse hypervisor again?
Sure. So traditional virtualization, you take a system and you break it into smaller pieces. What we are doing is we have broken what the physical boundary is on a server. What we do is we combine these systems. So the diagram kind of behind me here, we combine the systems. When they boot up, they communicate with each other, they talk to each other, and then we will say, oh, I have 4 nodes. We will then, to the operating system, represent all the resources of those nodes to the operating system. So all the the memory, all the cores, all the IO capability will then be represented as a single image and a single instance to the operating system, and a single instance of Red Hat or Oracle Linux or SUSE, whatever, will then be booted up on top of us.
Awesome. So you take multiple x86 servers and combine them into a single one.
That is correct. That's correct. And so of course the benefit, I think, kind of speaks for itself, but it really gets even to be greater, the benefit over time, because you don't have to predict what your needs are for the future. You can just grow the system as you go. So our system is self-optimizing today. I just showed you self-healing as well, and how we will identify errors and fix that. And then the step beyond that, which we will bring out next year, is around self-sizing, where the system will actually look and go, what is the optimal size system, and self-deploy. Now, some people ask, isn't this available in the cloud? Isn't this what the cloud does? Not at all. Not at all. The only way to get this in the cloud is to run us in the cloud. There is nothing else in the world that does what we're showing.
Great. Gary, thank you so much for the talk and all your support for the Hot Interconnects.
Oh, our pleasure. Thank you, Raj.
Awesome. Our next session right now is a poster by Facebook, and I'm going to present, share my screen right now. Actually, I am having trouble sharing it for some reason. Maybe I don't have permission. Let me try again. Yeah, I'm unfortunately, I don't have permission to share this. So what I will do is post the link to it, which is also on RD Mobile, onto the chat. Yep, I've sent the link over. Hopefully that works. I apologize for that. And if there are any questions, there are members of Facebook on the call, and you can also post it to the Slack channel, which I'm going to send out the link now. Just a second. I have the Slack channel for the poster for Facebook, and you can post it there. Any questions there? Well, that's all what we had today for sponsorship talks. Thank you, everybody, for sponsoring our conference this year. And I'm going to pass it over to Pasha. Is that you or Ryan?
Around, probably we will leave the